Hi, this is Dan. This is a solutions video for the free response supplement to the final exam in statistics spring of 2013. The first question is just to make a scatter plot of this data. So the X is the number of years they've studied Spanish, and the Y is the score on this exam. So we make this little scatter plot here, and I've drawn a line of best fit because the next question kind of need that. And it gives us the regression equation here. Essentially say if this equation is saying 31.55 plus 10.9 points per year. So that's kind of the slope. 10.9 is you're going to every year of study you'll go up 10.9 points on this score on this test. Obviously, this is correlational between years of study and performance on this exam. Then it asks for a residual plot here. The residual plot is just how do these points compared to the line that I've drawn here. So you could draw any line you wanted, and then you just make your scatter plot. So like this one's below, above, above. So I try to mimic that here just to show is the pattern of the dots around the line random, and if it is, it's probably a good linear model, and it looks like it is here. And how close are they tells us its strength. So this would be a strong positive correlation here. And if you want to predict for 4 years, what does this line predict, or this prediction equation right here? If you put 4 in for X, you get 75.15. And is this appropriate model for 1 year of study? And if you notice, the data starts from 2 to 5. And whenever we're doing any kind of regression analysis, we want to stay within the data. So any extrapolation beyond our data is dangerous. So that's why no, we should not extrapolate beyond our data to make predictions, because that can be very dangerous. Number 2 here, we've got a residual plot, kind of like the last one, but as we can see, this line of best fit, we definitely see a pattern here. And if I was going to predict the next one, it would probably be above. So that is not good. This is a non-linear model, looks like to me. So it says, does it suggest a bad model? Yeah, that's a bad model. Why or why not? It's because we have an observable pattern, and this definitely does not look like a random dots. We definitely have a pattern going on here. And number 3, a lot of people were fooled by this one. This is just roll a fair die 48 times. How many times should we see each thing? So 48 divided by 6. So we should see 8 occurrences in each one of these boxes. Obviously, we don't see that. The question is what we observe significantly different? So the hypothesis test, null and alternative. Your null is that it's a fair die. Your alternative is it's not. And we use a chi-squared test here. And if you look at your formula sheet for this, it's right here. Observe minus expected, and you square that difference divided by expected, and you add them all up. So if we go back here, we observed 2 occurrences of a 1. It should have been 8. So 2 minus 8 squared divided by what we expected, which was 8. And all these are expected to be the same, so they're all over 8. So just observe minus expected squared, observe minus expected squared. So I did that all here, and you get a chi-squared statistic of 25.25. And you're like, well, what does that mean? Well, we have to look at the chi-squared table. And if we go to row 5, because it's degrees of freedom, there's 6 categories. 6 minus 1 is 5. So look in row 5 of right here, and 25 is way over here. So yeah, this is a really whacked out die. Very strong evidence that it is not fair. We have observed much more variation than we should have. So we are going to reject the null hypothesis and say we have significant evidence that the die is not fair. Number 4 here, this is just practicing reading a printout from any kind of analysis. Honestly, this is the display, and pretty much the only thing you have to do here is read the p-value. And since our p-value, or the probability of us experiencing this much variation, should only happen by random chance about 1% of the time, that's definitely less than our 0.05 threshold, so that means we would reject the null because our p-value is less than our significance level. Obviously B and D, we never accept the null, so you can pretty much rule those out. And C, we do, and it says reject, it's greater than, the p-value is greater than. Well, if the probability is greater than significance, then we would fail to reject. So the answer here is A. And number 5, again, we have another goodness of fit, but this is with a table. And to calculate these expected values, you just take row total times column total divided by grand total. So there it is. 70 times 80 divided by 110 is the expected value for this cell. We do that for all four. Row total times grand total, row total times column total divided by grand total. And there's all the expected values. And then this is like the other one we did, chi-squared. Null hypothesis is insurance is independent of gender. It doesn't matter if you're male or female. The alternative is that insurance or having insurance is dependent upon your gender. We do the same thing with our chi-squared. Observed, we observed 50 here. We expected 50.9. We square that difference divided by what we expected. And here's the expected value for all four cells. And we calculate a 0.16 as our chi-squared. Very small. And if you look that up on your chi-squared table, degrees of freedom is row minus 1, columns minus 1. Well, there's only 2 rows, 2 columns. 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. So we look in row 1, and 0.16 is very small. It's way over here. So the probability of us getting this much randomness by chance is greater than 0.1. So pretty much we can say do not reject the null hypothesis. There's not enough evidence to say that insurance depends on your gender. In fact, the observed and the expected were almost identical for all these. And the last one, farmers said snowfall levels, they did not have significant evidence. And if we show our little distribution like we do, if there's not significant evidence, so let's say here's the 0.1 level, okay, so all this is 0.1. But they did not have enough evidence to say yields decreased enough. That means the test statistic ended up being somewhere over here because there wasn't enough evidence to reject the null. Well, it says, would you have made the same decision at 0.05 and 0.01? Well, for us to reject at 0.05 and 0.01, we'd have to have even more evidence. While if we didn't reject at 0.10, we definitely would not reject at these others. So they would have made the exact same decision, not enough evidence to say something's up. So that's the supplement to the final. There was 32 points on this, and the multiple choice was 22 points, had 54 points total, and I did a square root curve this year. So I took your percentage, just took, let's say you got 30 out of 54, so I'll just do that one real quick. 30 divided by 54, the scores were poor. That's a 55%. And then I take the square root of that, 0.5555, and that actually becomes a 75. So that's how I curved everybody's scores for this final. So my bad for, I'd say, the low scores. I did mix up this exam a little bit more, made it a little tougher, and well, I'll have to try to learn from my mistake, but that's how I curved the final, and I hope this helps you get ready for the subsequent final or explains more about what went on in that final exam, and it makes more sense now.